Welcome everyone. In this video lecture, we will solve a numerical based on the operational amplifier and it is from the Microelectronics circuits book. So the problem is for an ideal op amp, so there is an ideal op amp, we have to find or we have to derive an expression for the closed loop gain. Okay, means we have to derive an expression for the closed loop gain, that is our V naught by Vi for the circuit shown below. So this one is a inverting kind of amplifier. Inverting amplifier is there having four resistor R1, R2, R3, R4. Use this circuit to design an inverting amplifier with a gain of 100. So gain is, we have to make the gain 100 and the input resistance having 1 mega ohm. Okay, input resistance is 1 mega ohm. Input resistance. Okay, and we have to find the closed loop gain. Okay, derive the expression and having the gain 100, and we have to assume that the maximum resistance value will be 1 mega ohm. We cannot take the resistance value greater than 1 mega ohm, so we have to design the, or we have to means find out the value for R2, R3 and R4. We have to design. Okay, and finally we have to compare the design with the traditional inverting configuration, so that we will solve in this video. Okay, so the very first thing, the op amp is ideal. The very first thing is given, the op amp is ideal. Okay, op amp is ideal in nature, so we have to take the amplifier gain a open loop gain, that is should be infinity. Okay, so we have to go for the virtual ground concept. Virtual ground concept we have to apply. Okay, so this one is our inverting amplifier, so this voltage is 0, so this will be automatically 0 volt. Okay, this should be our 0 volt because this one is grounded. Now for the time being, I am saying this one is our I1 current, I am saying this one is our I2 current, and some current is going like this I3, and I am saying this one is I4. Okay, I have assumed some current. Okay, so first of all, what we will say, this one already we have taken a 0 volt due to virtual ground concept. V plus equals to V minus, that is our 0 volt. So directly we can write 0 volt. Okay, because for the ideal one, A tends to infinity. Again, I am okay. So every time I am saying A tends to infinity, we have to use virtual current concept. So this voltage is same as this of this. So we can find the value of I1. R1 resistance is there. Okay. So here I am writing R1. Okay. Some R1 is there, and I am saying this current is our I1, and this potential I am saying Vi, and this one is 0 volt. Okay, so simply the I1 value will be higher potential Vi minus 0 by R1, or simply we can write as Vi by R1 current will flow. Okay, say I am saying this one is question number 1, and there will be no current flowing through this. Okay, due to very high input impedance, there will be no current in this one. So I1 is same as that of I2. So one can write another thing, we can write I1 equals to I2 because all the current will go like this. Okay, so now we have to think about the resistor 2. Okay, so now we are thinking about the resistor 2, that is our R2. Now this voltage will be say 0 volt, and now I am telling this voltage I am saying Vx. Okay, we are assuming this potential is say Vx volt. Okay, so this current, that is our I2, is nothing but simply same as that of I1. Okay, so the expression for I2 one can write 0 minus Vx by R2, higher potential minus lower potential by R2. So this one is minus Vx by R2. Okay, or one can write the Vx value is nothing but simply minus I2 R2. Anything you can write. I2 R2, and I2 is nothing but simply our I1. Okay, so now Vx equals to minus I2 R2, and I2 is nothing but simply I1. So I2 is nothing but simply minus Vi. Okay, Vi R2 by R1. Okay, see, because this one I1 equals to I2. Okay, so now this I2 is this. Okay, this I2 minus I2. So one can write minus Vi R2 by R1. Vi by R1 for I2, and R2 is multiplied. So this one is the important result. So I'm just highlighting this one important result. This one is also considered important one. Vx we can say. Okay, it is very simple. And I2, how we are finding? Okay, we are doing for R1, R2. Here you can also directly I can write, but I am just now for the R3. Okay, so now for the I3. I3 means one resistance is there. Okay, I'm making. Suppose now R. Okay. Now this one is say I am saying R3 resistance, and this one is Vx, and this one is 0 volt. Okay, and I am saying this one is I3. So now I3 is simply 0 minus Vx by R3, or simply we can write minus Vx by R3. Simple network concept. Okay, and Vx we know, Vx we have find out. So minus Vx and minus Vi. So it should be minus minus plus plus Vi R2 by R1 R3. Okay, so now I3 is Vi times of R2. Okay, so this one again important result. So better to highlight this one. I3 value is nothing but simply Vi. Okay, means minus Vx by R3. Okay, this one means how we are finding. It's very simple. Okay, so once again I3, now we have know the value of I3. Now the current I4 I4 I am writing here. Okay, so it will be better to see this I4 is nothing but simply I2 plus I3. Just Kirchhoff's current law. KCL at this point, the I4 is outgoing current is the this incoming current I2 plus I3. So now I2 and I3 we know the value of I2. I2 we have I1 equals to I2 means Vi by R1. So Vi by R1 plus I3. I3 we can write it Vi R2 by R1 R3. So this one is the I4 expression. I4 equals to Vy by R1 plus Vi R2 by R1 plus R2. Okay. So this one is also an important result. So better to highlight. Okay. Now everything is, now we have to find the gain value. Oh, okay. We can say the overall closed loop gain. Okay, closed loop gain. That is our G. We have to find P naught by Vi. Okay. So now V naught is not involved in all these equations. So what we can do now? What we can do? We have to apply Kirchhoff's voltage law in this loop. Okay. Means I am saying this one is our V naught. So if we are applying like this Kirchhoff's voltage law in this loop, say loop one. Okay. So if we apply Kirchhoff's voltage law in this loop one, what we can write? By applying KVL in loop 1. Okay, why we are doing? Because this one is V naught. Okay, so directly what we can write, here I am writing plus V naught Okay, current direction is like this. Okay, okay, so V naught, then we are moving like this. Okay, opposite to the current, so we can write plus I4 R4 plus I3 R3. You can write as per your need, is how convenient. What is your convention? So plus V naught I4 R4 plus I3 R3. Now there is expression for V naught. So now V naught can be written as minus I4 R4 minus I3 R3. So now again V naught I4 value is now known to us. This expression, okay, with minus sign. So in both the term Vi is common. So I am taking minus here, Vi common, okay, and R4 is also there. So R4 if we take, okay, so first write 1 by R1 plus R2 by R1 R3 into R4 minus I3. I3, okay, I3 we have already find. So I3 minus, so Vi R2 by R1 R3 into R3. So this R3 cancel. So now final expression for V naught we can write as, now Vi is also common in both the term. Okay. So what we are taking, minus Vi common. Okay. Clear? Because we have to find the V naught by Vi. So now everything is in terms of V naught by Vi and R1 R2. So Vi if we take common, so what we can do here, R2 by R1 term is there. So okay, I am just first taking this term, R2 by R1, this term. Okay, this one is clear, R2 by R1. Okay, this part is over. Now R4 by R1. Okay, R4 by R1, if you take common R4 by R1 from both sides. So I am just directly writing R4 by R1 in bracket what we can write 1 plus R2 by R3. Very simple. Simple calculation by using R4, R1 outside, so 1 plus R2 by R3. Okay, so this one is the expression. So finally, what we can write, V naught by Vi H minus, now if we take R2 by R1 common in both sides, okay, from this one, so what we can write, R2 by R1 common in the this one. So R2 by R1, then R4 by R2, R4 by R2, then R4 by, then R2, R2 is there, then so take common R2, so no need to write, then R4, R1, R4 plus R3. Very simple. We have written like this. Okay. So this one is the final expression for the gain. Okay. Means the, we can say the closed loop gain. Basically the closed loop gain. This one is our closed loop gain expression. Closed loop gain expression V naught by Vi. So this is the way how to find. Very simple. Everything Kirchhoff's some virtual current concept. Okay. Now we have to design. Okay. So in the question it is clearly mentioned that the input resistance having value 1 mega ohm maximum. Okay. What it means? This the R1 value is 1 mega ohm. Okay. Input resistance means this one, this side. Okay, if we consider this resistance Zi, or sometimes we have to write so R1. Okay, so this one is the input resistance R1, and R1 value is 1 mega ohm. Okay, and we have to take the maximum resistance value 1 mega ohm. Okay, because we are assuming that for practical region, the resistance value cannot go beyond 1 mega ohm in op amp. Okay, now, so with the limitation of using the resistor no greater than 1 mega ohm, so R1 will be 1 mega ohm. So the maximum R1 we have assumed that 1 mega ohm. So now for this designing purpose, what we can say, we are saying we are assuming R2 as also 1 mega ohm. Okay, so this will be 1. Okay, and we have to make a gain with minus 100, gain with 100 dB gain. We have to design for the gain. Okay, gain of 100. Okay, we have to design for the gain of 100. So basically what we are doing, we are taking the magnitude. So it should be R2 by R1, the same expression, but we have to remove the negative sign. Okay. Okay, so this value will be 100. So this R2 by R1, I am assuming that this should be our 1, 1. So 1 mega ohm. Okay. So and this value is 1 already. So now if we again, I am taking R4 as also 1 mega ohm. So R4 by R2 is also 1 mega ohm. So R4 is also not. So R3 we can find. Okay. So some resistance value we have assumed for. Now we have to design for the 100 dB. Sorry, 100 gain. So what we can write, 100 equals to R2 by R1. So 1 by 1. Okay. 1 plus 1 by 1. Okay. And R4 is also 1. So what we can write, R3. So R3 value we have to find. So 100 equals to 2 plus 1 by R3. Okay, 2 plus 1 by R3, and all is mega ohm. So this one is basically 10 to the power 6. Here mega, so cancel. And this one will be in the what? 1 is unit. So this 1 plus 1, 2. 2 plus 1 by R3 means basically 10 to the power 6. Okay, means R4 is, and we are telling that is mega ohm, 1 mega ohm. So 10 to the power 6, 10 to the power 6, 10 to the power 6, cancel out. Okay, so it is simply 1. So 2 plus 10 to the power 6 by R3. So if you solve this one will be 98, then 10 to the power 6 by R3. So R3 equals to what? 10 to the power 6. So what I am writing? 1000 by 98 into 10 to the power 3. 1000 between 1000. Okay, 10 to the power 3 into 10 to the power 3. So 98 by 1000, it will come around 10.2 kilo. So R3 value will be our 10.2 kilo. So our design value will be R3 10 kilo 10.2 kilo ohm, R1, R2, R4 having 1 mega ohm for the design of 100 dB. Okay, so this one is the acceptable range of the resistance. So now we have to compare with the traditional inverting amplifier. For the traditional inverting amplifier, we know directly R2, R1, Vi, V0. So V0 by Vi magnitude we can write as R2 by R1. Okay, basically R2 by R1. So R1 is we are taking 1 mega ohm. Okay, so R2, and we have to make it 100. Okay, we have to make 100 gain. So R2 will be 100 mega ohm. So to achieve a 100 gain of having value 100, we need a very high value of this resistance, which is practically not feasible, 100 mega ohm. Okay, for the design purposes. So this one is required R2, but it can be resolved by taking this kind of structure. Okay, so R3 value is very less. So this is the solution for this question. So basically they are asking about all this data, means compare the design with the based on the inverting configuration. So R2 is needed in the traditional 100 mega ohm, so which is not possible for a IC design. and we have to find the R1, R2. So R1, R2, R4 we have assumed 1 mega ohm and R3 10.2 kilo ohm. So this is all about this question, and this is a very good question, and it is from the microelectronics circuit book. So thank you for watching this video.